Hello guys, welcome to my YouTube channel. So today we will be solving bi-weekly contest 117 problem C 2930 number of strings which can be rearranged to contain substring. Okay, pause the video, read the question, then we will proceed. Cool. So the question is saying that we will be given an integer n and we a string. There is a definition of a good string, and what it is, a string is called a good string if it contains letters such that if we rearrange it, it contains leet. So that's nothing but it should contain leet, so that after rearranging we can form this leet as substring. So that's the question is very straightforward. Okay, and we also have some example that LTER, so we can rearrange this in such a way that we will form leet over here, right? But if we don't have any leet, then we can't form leet. So what the question is? Question is we are giving this integer n. Now we have to tell how many strings will be there of length n that will be good. Okay, and the number can be very large, so we'll have to return a module. So in a nutshell, the question is return the total number of good strings of length n, and good string is nothing but the string which contains leet. So let now, so we have couple of ways to solve this, but we will talk on two approaches, or we'll see two approaches. First one is straightforward DP, and second one will be combinatorics. Combinatorics. Okay, so let's see first with DP, and then we'll move on to combinatorics. Okay, so now let's see what the question is saying. Question is saying that we'll be given an integer n, and we have to form a string, right? And this string should contain at least one L, two E, and one T, right? So that's what question is saying. Now, if we have to form a string of length n, that means we will have indexes like 0, 1, 2, 3 till n minus 1. Now, what we can do, we can put any alphabet A to Z on this index, similarly on this index, similarly on this index, similarly on this index. Okay, till the end. And if when we reach at the end, then we'll check how many A's are there, how many B's are there, how many C's are there. Similarly, if we'll check for this one, then we should have at least one L. L should be at least one. That is, the count of L should be greater than equal to 1. Similarly, the count of T should be greater than equal to 1, and count of E should be greater than equal to 2. Okay, so that's a very simple overview approach. Now what we can do is at each position I, we will just try to put A, B, C, D, E, F, right? And we will increment the value. We'll increment the value of A, of B, or by C. So now the only question is remaining: how we'll increment the value, or how we'll store this. So how we'll store that? So first of all, if you'll see the value of n, it is 10 to the power 5. Now, if we'll think that we'll store the count for every character, that is like for A, for B, for C, for D, right? So we know that each character can be same. So for A, let's say all the 10 to the power 5 characters were A. So this maximum value can go to 10 to the power 5. Similarly, this will also go 10 to the power 5. So we cannot apply DP in this manner. Okay, but we have one important observation, one very important observation. What we don't, it doesn't matter for us what is the number of A, neither B. The only thing that matter is whether L is one or not. I mean, technically, if it's greater than, then also it's fine. But at least it should be one. Similarly, goes for T. T should also be greater than equal to 1, and similarly goes for 2. E should be greater than equal to 2. That means, let's say if we already have L, 1L, then we don't, it doesn't matter whether we increase the count or not. Listen carefully what I am trying to say. So let's say if we have something like this, right? That in the end we will check, or it's better. We'll have three variables: L, E, and E. We'll keep count of only these three variables. So let's say I is equals to 0 till, let's say, n was 10. So it will go till 9, right? So let's say in total there were 3L. But let's say if L is equals to 1, at I is equals to 1 itself, there is one L, so we can simply mark this as L as 1. Now in the next time we know that this L is already 1, so we won't increase it, okay. Similarly, if for T as well, if there was already, if it was 0, if T was 0, that means if we found a T, then we'll increase it by 1. But if it's already one, then we don't need to increase it, because let's say if there was some string S is equals to something like TT LEEEE T O O, it doesn't matter how many times T we have, we just need one. So if we have T equals to 0, that means we haven't found any T. But if we found any, we'll make it as 1. And if we have found one T, then it doesn't matter how many T we get, so we don't need to increase this as well. Similarly for E, initially it was 0. Let's say here we found one E, then we'll make it 1. Here we found another E, then we make it 2. And let's say we found another E, then we don't need to increase it. Why? Because we only need two E's, and we already have it. So if we'll see over here, that the dp we are discussing here, right, the dp we are discussing here is drastically reduced. Initially what we were trying to do was storing the count of A, B, C, everything. But now what we have to store, just indices, or let's for the timing leave indices. So the count of L, the count of T, and the count of E. Okay. And in this also we know that L can either be 0 or 1. Similarly T can also be 0 or 1. Similarly E can be 0, 1, or 2. So our dp is drastically reduced from, I don't know how many, like 10 to the power n plus 1 times 2, simply this one, 10 to the power 5 multiplied by this one, 2. The range is 2, the range is 3. So this is nothing but n, and this is nothing but 4 into 2, 12n, something like this. Now how can we implement this? It's very simple. It's standard dp problem now. So what we'll do, we can simply run a dp, let's say dfs or anything we want. We'll have index, we'll have count of L, count of T, count of E. Okay, we'll simply run a loop for, let's say, char c is equals to ch is equals to, let's say we start from a small a, because we have already only the small alphabets, so less than equals to z, and ch plus plus. Now if, so first scenario, if L is equals to 0, and this ch is equals to L, then in that scenario what we'll do, we'll increase this L. So what we can do, we can pass it from here like dfs of I plus 1. Okay, I plus 1, and we'll increment the count L plus 1, and similarly leave the T and E as it is. Similarly we can do for E as well. For E, what we will write, if E is less than 2, E is less than 2 and ch is equals to E, then we'll increase the count. Okay, else even if it doesn't matter whether it's L or I mean, let's say if it was A, B, C, anything, in that scenario we don't do anything, we simply increment it a I plus 1, that is we move to next index. I mean, if we have something like 0, 1, 2, 3, 4, 5 till n, so if we check this index and this was A, we don't have to do anything, we can simply go and see at this index also we are running a loop for A is equals to, something like A, we are running a loop that will run precisely 26 times. So eventually our time will increase, but for the timing, let's ignore that, we'll calculate that later. So what we'll learn from here is, if it is any character other than L, T, or E, then we can simply increment the index because it won't change anything for our final condition. Else, if it is L, T, or E, then we will check if for L, if the value is 0, then only we'll consider incrementing the value, else not. Similarly for the T, and for E we'll check if value is less than equal to 2, then we'll less than equal to 2, sorry, value should be less than 2, either it's 0 or 1, then we'll increase its value, else we won't. So that was very straightforward approach for this one. And now if we'll see this one, this will take very big time complexity. It will be like something, see here it is 10 to the power 5. Okay, and for this, and for here it is 26, and here we calculated this 2 p, I mean sorry, not this one, this will go exponentially, right? Like each level will have 26 branches, right? But in total if we'll assume dp over here, so it will become something like dp E, right? And at each position or each configuration, I should say, for this ILTE, we will run this loop 26 times. So in total, it will become something like 26 multiplied by whatever value we have calculated earlier. That is 12n. So 26 multiplied by 12n. So I don't know how much that is, but you can calculate. Now let's see the its code. Okay. So what we have done nothing. First of all, we check the condition that if the character is already less than 3, then we can't do anything and we can simply return 0 because there won't be 4 characters to form lead. Else we have initialized, let's forget the DP. So first of all, what we passed the index, pass the value of n, pass the count of L, T and E, or sorry, E, L and T. Now we checked if we reach the last index, that means we don't need to put any characters anymore, and we'll check, we can simply check if e is greater than 2, l is greater than 1 and t is greater than 1. If all these conditions satisfied, then yes, this was a valid configuration and we can return 1, else we can simply return 0. Similarly, if yeah, and then again what we did, we run a loop, like let's say if we are not at the end, let's say we are at in some middle of this, let's say out of n minus 1th position, 0th position, we are somewhere here or anywhere, doesn't matter, any valid index. So we'll simply run a loop, like we can put any characters over there, right? So in the example I was explaining using the characters, here I have just used the index number as 0, 20, 1, 2, 3. So e will be position 4. So if we are putting e over here, that means for I is equals to 4, if we are using that I at value 4, then what we'll do, we'll check if e is less than 2, then yes, we'll increment the count of e by 1 and increase the index. Similarly, we'll check for all the condition, else if none satisfied, we'll simply increase the index. Okay, and we can see we are also implementing dp over here so that it won't get any TLE. Okay, so this was an AC solution. Now I hope this would be clear. Now there is another solution, and that is combinatorics. Like, I mean, most of you guys would have also thought that maybe how can we think it from the PNC point of view, that is permutation and combination points of view. So let's say how many strings we can form of length n containing small alphabets. That will be nothing but 26 to the power n. I'll explain. What I'm saying is, let's say I said you make a string s of length 1, so how many string you can form? Either you can put a, b, c till z. So the number of strings in this scenario will be formed 26. But if say I said for length equals to 2 or n equals to 2, if n equals to 2, how many strings you can form? Similarly, you will put a over here in the first position and all the 26 characters in the last position. Similarly, we will put b over here and then put all the 26 characters. So it is nothing but 26. Okay, or if we'll write this as something, it will become like 26 here, then 26 here, then till 26 till z, right? So in total it's nothing but 26 into 26. Also you can see something like that we have these two positions to fill, and here also we can put a till z. Similarly here also we will put a till z. So if we have something like this, three characters, then we will have also have a to z to fill this place. So for this we have 26 option, for this we have 26 option, for this we have 26 option. So let's say this was n minus 1th. Okay, starting from 0, or if we are starting from 1, we can simply take this as nth. So here also we'll have a to z, that is 26 option to fill. So in total how many strings we can form? 26 to the power n. Okay, so if we consider this as universal space, or let's not use this universal space, it's PNC terms. sample space I want to say. But so let's say if this is the total possibilities, right? And we know that how much this can be. This can be 26 to the power n if we have length n. Okay, just let me clear one this or okay, I'll just make a new one. Just a second, guys. So let's say what I'm saying is this is our sample space, that is nothing but 26 to the power n, the total number of possibilities. Now, now, so we know that total number of strings is nothing but 26 to the power n. Now let's say I am saying that we know that, right, that in our string or the input string there should be exactly sorry, at least one l, right? There should be one l, there should be one t, and there should be two e. Now what I'm saying is that if I am not using any, if I am not using any l, then how many strings will be there? Listen carefully. What I am saying is, if I am saying that if I am not allowing you to use any l, that means that means for this, like we have n positions, right? 1 2 till n. Then for each position we'll have a to z except l, except l. We won't be using l. So for each position we will have 25 choices to fill, right? We'll have 25 choices to fill. So in that scenario, we will, how many strings are there without l? How many strings are there without any l? That is 25 to the power n. Listen carefully, I will repeat. What I am saying is that I am saying that form a string of length n but without using any l. That means for each position initially we have 26 choices from a to z, but now we have only 25 choices from a to z because we have removed l. So in total, if we have n places to fill with 25 choices, right, so it will be nothing but 25 to the power n. Okay, so that was some scenario if we have excluded this l. Okay, similarly same thing goes for t. If I said that how many number of strings would be there such that there will be no t, then again it will become 2 to the 25 to the power n. Okay, now for e scenario, or for the case of e. Now for e we'll have two cases. First of all, 0 e allowed. In that scenario what will happen, that I am saying that fill this n position using 0 e or no e. Then again it will be nothing but as above, 25 to the power n. Okay, 25 to the power n. But now I am saying that let's say if 1 e is allowed, 1 e is allowed. Okay, 1 e is allowed, that means how many substrings are we can form with 1 e. So let's say if there were n positions, right? If there is one position, if I'll just fill this one with e, if I just fill this one with e, that means for this remaining position, how many positions are there? N minus 1 positions, right? This is 2 3, this was first position, 2 3 still n. So and for this we have 25 choices a to z but no e, right? So that will total number of strings such that e is fixed in the first place, and we have n minus 1 position to fill with 25 characters, so that will be nothing but 25 raised to power n minus 1. But one thing we have to keep in mind over here is we are fixing e over here, right, on the first position, but e can be fixed over here, e can be fixed over here, e can be, sorry guys, e can be fixed over here, e can be fixed over here, at in any of the n positions, right? So the total number of string with one e will be nothing but n multiplied by 25 to the power n minus 1. I'll repeat again. What I'm saying is, so first of all what we saw, that how many strings we can form using one e such that e is fixed at the first position. Then we got that 25 to the power n minus 1. Now we know that this e we don't have to fix it to the first position, it can be at any position. And in total if you are fixing e at over here, we getting 25 to the power n minus 1. If we'll fix e over here, that is at second place, then also we'll have 25 to the power n minus 1 strings. Okay, so in total we will have n position to fix e. So the total number of string with one e will become nothing but n into 25 to the power n minus 1. Okay, so till now what we have calculated, we have calculated if no L is taken, if no T is taken, if no E is taken, if one E is taken, there are again scenario, right? If there are no L and no T, then also what will happen if I am saying that how many strings will be there such that there are no L, no T, then in that scenario what will happen? So out of for all this n position, we'll have only 24 characters left, right? So the number of string without L and T will be nothing but 24 to the power n. Okay, now we again have similarity, we again have one possibility that we have no L, no E. Then in this scenario, we'll have 24 to the power n. But let's say if we have one no L, but one E is allowed. One E is allowed. Okay. So in that scenario also, what will happen? First of all, we have this one scenario, and here it will have what will happen, that will fix one E at any position. So like let's say 1 2 3 till n. So in one of the position, let's say we fixed it over here. So for this 3, what many we'll have 24 to the power n, and this we have already calculated from here that it will be nothing but n multiplied by 24 to the power n. Same goes for like te. If there is no T, no E, we will have 24 to the power n. And if we have T and 1 E, then in that scenario, n into 24 to the power n. Now, there will be one case where no L, no T, no E. That will be nothing but 23 to the power n. Now, the important question is, why are we calculating this? So let's say if there is a string, when it can be bad, if there is no L, right? Or if there is no T, right? If there is no E or one E, okay, if there is no E or one E, so all those strings will be bad. Even if there is no L, no T, because see, in this, if there was no T, maybe there can be L, right? But if we are confirming that there is no L, no T, then also we'll similarly all the cases, or let's say what I will say. So what I'm saying is, we let's see this as three conditions. One is A, one is B, and one is C. A is nothing, but L should be equal to 0, or L is 0. B is nothing but T equals to 0, and C is nothing, E less than 2. So if any of this case is satisfied, that means we will not have a good string. So if we'll see the total number of strings, right, for this kind of scenario, that is either of these conditions satisfied, this is nothing but A, or the count of A plus count of B plus count of C plus count of AB when both the conditions are not satisfied, plus count of BC plus count of CA minus count of ABC. This will be more visualized. Let's say if this was the sample space, right, that was nothing but the total number of string we form, and this is the space where L is equals to 0. Now this is the space where T is equals to 0, and this is the space where E is equals to 0. Okay, now so if we'll see over here, what we'll realize that even if there is some L, right? See, in this scenario, let me choose this one. So see, apart from this circle, like outside of this circle, we can have L, as many L, right? So, but in this scenario, in this circle, we are not considering any T. So let me explain again what I'm trying to say. So if you observe carefully, what we are saying is that in this circle we have 0 L. So out of this entire strings, that is the total number of strings, we can simply remove these many strings, right? Because we know that if there is no L, we won't have any condition, or we won't have any good string. And here also it is less than 2, not 0. It is less than 2, it can be 1. So this can be true. Okay, if this is true, then also we won't take any we will simply remove all these substrings, all these sorry, strings, because they won't be good. Same goes for this t. We will remove this one entire. Same goes for this condition as well. This is e less than 2. But if you would have seen, or if you observe carefully, this is basic set principle. What we are doing is we are taking this reason twice, and similarly this reason twice. Okay, so we are taking this reason twice. So, but we can't take this reason twice, right? I mean, this is a common reason. This is a common reason. So, so what we actually have to do is, or make me a better figure again. So instead of taking this reason twice, what we can do, we can simply see, we can take this one, we can take this one, we can take this one. That will be nothing but S of A. If this is condition A, this is condition B, this is condition C. So if we'll take this entire portion, that will be S of A. Again, if we'll take this entire B, that will be nothing but S of B. If we'll take this entire C, that will be nothing but S of C. Now, if you'll see that if we take this entire A and entire B, then we have taken this area. This is nothing but intersection of A and B. For simplicity, if we'll take this area, we have taken it twice. So what we'll have to do? We'll have to subtract this one, right? S of A or B, because here both of conditions are S of A and B, I would say, not A and O or B, A and B. Similarly, this area we would also have to subtract minus S of B and C, and similarly minus C and A. But you'll realize soon that there is one portion which is center. Let me make again. So this common. So this common area, we would have subtracted this when we are subtracting this one. When we are subtracting this one, or removing this one, and again when we are subtracting this one. So we have subtracted this 3 times. In total, why we have calculated it 3 times, like when we are seeing this one, taking this one, taking this one, we have calculated this common portion 3 times. When we remove this portion, this smaller portion, we have already removed it 3 times. Then we have to add it 1 time, because we will have to take it 1 time, right? So we can simply add S of A and B and C. This is simple set theory. If you'll read, you can find it more. So sorry, here I have written it by mistake. It will be minus minus minus, and this will be plus. Sorry for the mistake. Okay, so but now here you have idea that we can simply calculate this one, we can simply calculate this one, and we will good to go. And we already know how to calculate this one. It will be more clear if we'll see the code. So what we did, first of all, we have calculated the total combination, that we know that 26 to the power n. If L is 0, we take no L, then it will become 25 to the power n. These are all the conditions that we have discussed. Okay, maybe if we have missed some condition in the discussion, but I think you will got the idea, right? And there is one more thing, this power function. If this is n, can be 10 to the power 5, right? So it's better to write a custom function uh, that will calculate the exponentiation in log n. This is nothing but modular exponentiation. If you want, I will make a video on that. Just comment it out. Okay, uh, that means tell me in the comment section, not comment it out actually. And also we have used the mod p. So that's nothing but to calculate the power. And finally, whatever we talked, we subtracted few values, and finally we added some values. So that's nothing. And finally we return the mod of this. This is also an AC solution. I hope both the solution would be clear to you, but if you guys have any doubt, let me know in the comment section. Thank you guys. See you in the next video.